Hello everyone, thanks for joining my talk. My name is Luca Visinelli from GRAPPA, University of Amsterdam. Today I'll talk about Axion Miniclusters, stellar disruption and radioastronomy. First of all, I would like to mention that my review, The Landscape of QCD AXION Models, is now available on Physics Report. This is work done in collaboration with Luca Di Luzio, Maurizio Giannotti and Enrico Nardi. So the outline of my talk would be the QCD axion as a dark matter candidate, stellar disruption of axion miniclusters, then we'll move to axion radioastronomy in the near future. I begin my talk by defining the concept of the weakly scalar interacting particle, or WISP, which is any scalar boson coming out of an extension to the standard model. The potential appearing in the Lagrangian here is rather general. WISPs could very well be the dark matter. In fact, their energy density, rho phi, scales as the inverse Hubble volume, which is what is requested for a field in order to play the role of the dark matter. The best phenomenology of WISPs interacting with gauge bosons through dimension 5 operator and with fermions through dimension 4 operator leads to a wide range of possible detection strategies for these particles. The archetype of the WISP is the QCD axion. This particle is related to the solution to the strong CP problem, which can be read as the fact that there is no observable CP violation coming from the strong sector of the standard model, despite there is a possibility for CP violating terms to arise within the theory. In particular, the theta value that regulates the CP violation in the strong sector has been bound to be smaller than 1 part in 10 billion. A solution to this problem has been proposed by Roberto Peccei and Helen Quinn, which promote theta to a dynamical field which is subject to a potential that naturally drives the values of theta below the CP violating observed limit. The QCD axion is the pseudoscalar boson associated to this theory once it's been quantized, and it has been proposed by Weinberg and Wilczek separately. The dimension 5 operator that describes the axion coupling to gluons is regulated by the axion energy scale Fa, which is inversely proportional to the axion mass Ma, as in the box here. The proportionality constant is related to the QCD confinement scale lambda QCD. The axion field follows an equation of motion that takes into account the Hubble drag and the effect of the axion mass. So this is equivalent to having a damped pendulum. So for early times, the mass term is not important, and we have a dark energy behavior. So a solution to the equation of motion is that theta dot is 0 or rho is constant. Then, at some point, when the Hubble rate is of the order of the axion mass at the time t oscillation, the oscillations in the axion field commence, and the field behaves coherently as a dark matter component of energy density inversely proportional to 1 over the Hubble volume. So not only the axion can be the dark matter, but there are large inhomogeneities in the axion field that come from the fact that we have a random initial condition. And this leads to gravity-bound objects that are called Axion Miniclusters, whose typical mass is of the order of the asteroid mass and the radius that of the order of the Sun to Earth distance. Numerical simulations of the spectrum of energy of axions over densities around matter radiation equality are needed to initialize n-body simulations, which assess how axion miniclusters merge hierarchically to form larger structures. This has been done in recent papers that have derived the halo mass function of axion miniclusters, or the distribution of axions with their mass. The results are in line with what is obtained from semi-analytical methods like the Press-Schechta formalism. This is important to us because we will use these results as a building block of our analysis. We now ask ourselves a key question. How many axion miniclusters are there in our galaxy? Axion minicluster could be easily disrupted by any stellar object passing nearby. So a star that goes by some impact parameter b near an axion minicluster with some velocity v would rip apart the fluffy structure of the axion minicluster, especially if this is near the galactic center where the stellar density is extremely high. This is a key question that we try to assess in our studies. This problem is what I have set up with Thomas Edwards in Stockholm, Bradley Kavanagh in Spain, and Christoph Weniger in GRAPPA, University of Amsterdam. So we have built a Monte Carlo simulation that takes into account the tidal disruption of axion miniclusters by all of the stars that compose the bulge and the disk in the Milky Way. We have initialized our halo mass function with the M-body simulation that has been derived from M-body simulations, and given that, we have run our Monte Carlo to disrupt any axion minicluster that goes too close to any stellar objects that we put in our simulation. In this way, we have come up with the halo mass function once the disruption by stellar objects is also taken into account, as I show in this cartoon that gives the relative populations of axion minicluster before and after the disruption. Axion miniclusters in our simulations are set on elliptic orbits with the focus on the galactic center. So one way to show results is by plotting the survival probability as a function of the semi-major axis of such a galactocentric orbit. So for survival probability, we mean how many axion miniclusters are there at a specific semi-major axis with respect to how many of them have been our simulation has been initialized with. We have considered different possibilities for our axion miniclusters. In particular, we have set both eccentric in solid and circular in dashed line. And we have also considered different density profiles for each axion minicluster itself, either a power law or NFW, which is more appropriate for larger axion minicluster built out of a hierarchic merging of a smaller one. The dot here represents the distance of the solar system from the galactic center. And we see that for power law circular, power law shaped axion minicluster in circular orbits, the survival probability is order 1, is about 100%. And then it degrades for different choices. But still, for the most pessimistic choice of an NFW, in which the axion miniclusters are in eccentric orbits, we still attain order 30% survival probability, which means that there are still axion miniclusters that can lead to interesting phenomena around our solar system today. An interesting application is our accompanying project, Axion Radioastronomy with axion miniclusters. We know that axions are converted into a radio signal within the magnetosphere of a neutron star. This signal can be potentially detected at Earth. Here, we model the magnetosphere of a neutron star according to the Goldreich-Julian parametrization, which describes the magnetic field and the plasma surrounding a neutron star. In this model, axion conversion is possible when the plasma frequency is of the order of the axion mass. But consider now a neutron star rotating around its axis at some distance d from Earth. An individual neutron star of this type is a perfect target for observing potential radio waves coming from it, which can yield information about the possible presence of axions in its surrounding. Current measurements have been already used to place bounds on the strength of the axion-photon coupling thanks to this method. We now come to our results. We do not consider individual neutron stars, but rather the collective effect coming from all neutron stars in the Milky Way. These neutron stars could encounter axion mini-clusters, where the density of axions is extremely higher than in the surrounding environment, and trigger axion photon conversion such that a signal could be detectable at Earth. In more detail, there are no axion mini-clusters in the galactic bulge, here, while the encounter rate becomes slimmer as we move further out from the galactic center, here. Such, for that, there is then a favored region in which the encounter rate is maximum, which we identify as a ring at around 4 kiloparsec from the galactic center and laying on the disk. We study in more detail the signal from axion conversion by plotting the peak flux on the y-axis versus the encounter duration on the x-axis in seconds. The peak flux is governed by the density of an axion mini-cluster, while its radius determines the duration or the time that the neutron star spends within the mini-cluster itself. For the Ampere population, which is this orange blob, the signal is of order 1 to 4 microlensing and can last up to 10 to the 9 seconds. These events are due to the dense, large mini-clusters, which are unfortunately removed when tidal disruption by stellar objects is taken into account. Fortunately, shorter but still relatively bright events still occur even when the perturbed population is accounted for. And this is a good news for detection hopes. So, conclusions. It's an exciting period to work on compound objects and on axion dark matter. We are really getting there to understanding how substructures are distributed in the Milky Way and how we could use these substructures to probe axions, the existence of axions besides direct detection in the laboratory. Thank you for the attention.